events. Next week, there's going to be a pen tester guest lecture here. She'll bring a laptop with Kali and Burp Suite. She'll have some kind of Burp Suite-based project, which is quite appropriate for this class for you to do hands-on. And lockpicking is coming up near Halloween, here on October 29. So that's a Tuesday. So you have to come here physically, and you can get extra credit in any of my classes by practicing picking locks. All right, so let's go on to the chapter. So we're going to talk about session management. So once you have logged in, you get some record of the fact. Typically a cookie is stored on your machine recording the fact that you've logged in. And then you're going to have to somehow maintain the fact that you've logged in and that you're different than other users, which is a little harder than you might imagine it would be. I think I'll move this over and look better. All right. So if you're able to defeat session management, then I'm able to take over someone else's login session. They've logged in. I don't need their password. I steal their cookie or other token, and now I'm in as them. Sometimes it can be as simple as just changing the value of a token. Your token might be short, like I'm 1001. So if I just change it to 1002, I might be in some other user's session. This happens a lot. It happened to me at DEF CON. I went to DEF CON and logged into Gmail around 2011. And at that time, I didn't know this, but Gmail was only using HTTPS to send your password. And after that, it would send you an authentication cookie without HTTPS. So these guys had written a tool that would steal that off the wire, and they get in your account. So I was on the Wall of Sheep. The Wall of Sheep is a very famous thing at DEF CON where random people can connect to the DEF CON network and they can monitor the traffic. And if they find somebody's login information, you put them on the Wall of Sheep to humiliate them for having used some insecure protocol at DEF CON, and that happened to me. So you got to have state. Now the problem with web is HTTP is fundamentally stateless. You send one request to the server gives you a response, and that's it. It's over. It doesn't remember who you are. If you send another request, it just regards you as another completely independent user. So this was okay for the original web, which is like my web page. My web page just has videos and lectures and stuff, but you never log in anywhere. It doesn't remember who you are. You might as well be just pieces of paper stacked on a bulletin board. You look at it, it just sits there. It doesn't interact with the viewer at all, except for the scripts that you use to send up automated grading for the CTFs. This is stateless, and that's the Web 1.0. That's what the web was designed for. In order to move to Web 2.0, where you actually have logging in and users can post content and stuff, you have to somehow remember who they are. So you have to somehow remember that you're authenticated. And you can also use sessions even if you're not logging in for things like items in a shopping basket or something. But the main thing you do is when you first connect to the server, and especially when you first log in, it will have a set cookie header, which will tell your browser to store this data in the browser. So it'll have the name, this is ASP.NET Session ID, and then it has a value. And each subsequent request from the client, if it's going to the same domain that set the cookie, it will include the cookie. So the data will be sent from the server and bounce off your browser and go back to the server. And this is how you create a session object in the intrinsically stateless HTTP protocol. So now it can remember that you are different than other users and that you have done something special, like, for example, logging in. So there's categories. You can either generate session, two ways to do this wrong. One is to generate session tokens in a way that they're predictable, and the other is to handle them in an insecure way so they can be stolen. And it was the second one that got me at DEF CON. Google at that time was sending this session token unencrypted over HTTP so anybody that could spy on the network traffic could steal it. They don't do that anymore. Shortly after that, they changed. Now it's HTTPS all the time, so that attack would no longer work. So sometimes it generates a token but doesn't really use it. This is very common. Websites often have tokens that don't indicate you've logged in. They just indicate to remember who you are so they can target ads based on what you click or something. So if you want to find a token, what you do is establish a session, replay the request in Burp, and then delete each cookie until you find out which cookie is used to identify who you are. I've done this to see which cookie is important on websites. That's Burp Repeater is a good tool for that. So I went to Amazon.com and I logged into something, and then I went to my original request, and it had down at the bottom, see, SAM CCSF's Amazon dashboard. So the original request knows who I am. It has my name down there. And it has a whole bunch of cookies, session ID and XWLUID and XMain and SSAtMain and SSTMain, and I don't know what they all are, but I just delete them one by one until it forgets who I am, and therefore I can decide which one is actually carrying the information who I am. So what I found was the only one you actually need is XMain. XMain, all the rest you delete it, it still knows who I am. So that's a way you can winnow down a complicated modern web request that has many cookies for many strange purposes down to the cookie that has the purpose you care about. All right, there's other ways to do this. There are other browser features. There's basic authentication, digest authentication, and NTLM authentication that add some form of a username and password to every request. They've been around for a long time. They're not used in the internet much. They're mostly used on local area networks and old Windows-based networks. And then there are sessionless state mechanisms where instead of having a session token, it just stores a bunch of extra data in something like an ASP.NET view state, which could be whatever data they want to know about you, like which items are in your shopping basket or something like that. And you can specify it this way on the server. This is ASP. So a sample array list, you'll have result add item 1, item 2, item 3, item 4. It looks like this is going to be a shopping cart. So you have array list. This is creating a view state object, which will be sent as a cookie to the user. And so you can store strings, Boolean values, list objects, array objects, and other things. All kinds of data you can store there. You can store just a bunch of data, which is sent to the user and echoed back to you with every request. So this is called the view state. And if you don't protect it, then the user could use burp to unpack it and modify it. So you should use view state. You should have it should be encrypted and signed, or at least signed. View state uses base64 and a hash made from machine authentication code, which will tied to the machine MAC address, so the cookie will no longer be valid if you move it to a different machine, and it will cryptographically verify that the data has not been modified, and it will enforce a session timeout by including the time in it. So this is much more secure, where you send data and you have much higher reliability, much higher assurance that when the data comes back from the client, it has not been modified. So if you want to find these things, you'll find token-like data items bigger than 100 bytes, a new item in response to every request because it's storing a bunch of data that keeps changing in there. Data is encrypted or signed, and the application won't let you copy it to the repeater and send that again. The second one will be rejected because it's tied to each request. Each request is individual. These are clues that it's using one of these sessionless state mechanisms that stores a whole blob of data on your machine. All right, so you might have trouble generating the token. This happened to Facebook. Facebook found that password reset would email you a 6-digit code, and the guesses are rate limited on one site, but they were not rate limited on some beta site. So you could try 1,000,000 guesses, which is what it needs to guess a 6-digit number. So he was able to get him in Burp Intruder and made a $15,000 bug bounty for that. It's a simple one. All right, so here's common cases. You email someone a password recovery token. You also often put random tokens in hidden form fields to prevent cross-site request forgery. This means that nobody can forge the request. The only way to make a request that will be accepted is to actually have the official page, like the login page from the server on your machine, and have one user log in directly from a browser, because that form has a hidden field which changes all the time. So if you use something like Burp Repeater to send a forged request, it won't accept it. Token gives you one-time access to protected resources. You can have persistent tokens used for Remember Me. That's the most common thing, a cookie stored on your machine. And you can see the status of an order and so on. There's just anytime there's a piece of data relevant to the browser that you want to send from the server, you can use one of these tokens. Now, all these tokens have to be unpredictable, so people can't just take the token on their machine and modify it to get somebody else's token. So this token may appear to be random, but if you know your ASCII, you'll recognize it's just hexadecimal. 75 and 73 and 65 are printable ASCII characters. So if you reverse this from hex back to ASCII, it's user equals daf, app equals admin, date equals this. So now you could easily generate a token that says user equals admin when perhaps get in as the administrator. This is not good. This doesn't prove you've logged in. because it's easy to read and modify. That's why this is a very unwise procedure to store important information just encoded but not encrypted. And so that's the ASCII table. And here's user. The 70s are lowercase letters largely. All right, so you might put in the username, a numeric identifier, email address, a timestamp, client IP address. These are things that might be in a structured token, including this meaningful data. And you might encode it with XOR or base64 or hexadecimal. So if in order to see if they've done this, obtain a token and modify it in systematic ways. Change it 1 byte at a time or 1 bit at a time, resubmit it to see if it's still accepted, and then you can perhaps discover some fields. And Burp Intruder has an automator for this called Character Frobber to change the bits 1 by 1 and send it up there and accumulate all the responses so you can see which responses are still accepted. And if it's a meaningful structured token, you can probably find some part of it that doesn't matter, like the timestamp, and change that quite a bit with having no effect. Log in several users at different times and record the tokens, register similar usernames. This is how I got into Stitcher. Stitcher was using simple Caesar cipher to encrypt passwords. So I just, or username and password, so I created just passwords in a pattern like this, and I could see the pattern in the so-called encrypted data going up, and so on. You can detect if it's not really doing a good job of encryption, like using AES or something, but it's instead just using one of these silly procedures like URL encoding or base64, or a modification of them. So look for tokens that are similar. Repeating a series of letters is often helpful. One trick I learned from your book is to make a username that is 32 A's, because then even if it breaks it into blocks of 16 letters and uses AES, I can still see that it's repeating. The first 16 bytes will match the next 16 bytes, and that shows they're using AES in electronic codebook mode, which is a weakness that can be exploited. Anyway, so I tried to use this pattern, try to guess tokens of other users, try to send a bunch of requests using these guessed tokens, and see if any of them reach somebody else's account, and then you have managed to defeat their token generation. Now what they ought to do is generate a long random token that will never be, and there's no reasonable way to modify one of those to find another valid one. That's the right thing to do, but a lot of people don't do it. So let's try a Kahoot. Looks like I don't have them open yet. All right, there it is. Maybe it. The few, the proud. All right, so what encoding turns that into this? MD5. This is much longer than the input. This is in fact fixed length. MD5 is 128 bits, so that is 16 bytes, so it's 32 characters of base 64. See, if you look at, not base 64, but hex. So if you look at this, it has numbers and letters, but only from A through F, and always lowercase. That's hexadecimal. So each one of these characters is 4 bits. This is a byte, and there's 16 bytes. That's MD5. MD5 always combines any kind of string of any length down to that. So that's a thing to be aware of. If it was any of these others, it would be approximately the same length. Base 64 only increases the length by about 30%. All right. So the fact that it's much longer gives you a clue that it can't be any of these. All right. But encoding turns it into that. Hexadecimal. You can tell because the AAAA turns into 41, 41, 41, 41. Each letter is turning into 2 characters of hex. Now, Jer is getting connection problems. Let me check from my end. According to this, my bandwidth is fine at this end. You might want to refresh your browser. And also what some students have told me is sometimes if you go into Twitch, there are settings here where you can change something about the quality and such. So you can change the settings in your browser to perhaps optimize for your network conditions. And refreshing the browser is something I often do when Twitch doesn't work well. So I hope that helps. All right. Anyway, all right. So that's it. That's hex encoding. That's just turning each letter into one byte, which is 2 hex characters. And after a while, you get these memorized. 41 is capital A, and the 60s and 70s are lowercase letters. Anyway. All right, how about this? What will turn it into that kind of stuff? That's base 64. You can tell base 64 because it uses uppercase letters, lowercase letters, numbers, and symbols. So you won't have Q in anything based on hex. You just have A through F. The use of the entire alphabet and using upper and lowercase characters is a very strong indicator of base 64. Because there are 64 possible characters that are used. That's where the name comes from. So it's 26 lowercase letters, 26 uppercase letters, all the numbers, and then a couple of symbols like plus and minus. That's what base 64 looks like. All right. All right, how about this? That's XOR, and you can tell because the AAAA turned into 05050505, and that means it's a simple translation. Each character turns into the same other character, but it's not the right character. Instead of being 41, it's 05. That's what XOR does. It takes every character, turns it into a byte, and then flips some of the bits. So that's XOR. All right. BK, I hope you know who that is. It might be real initials. Joel looks like a real name. That's W something. My grader may know who you are. You may not. So let's go back to the slides and carry on here. It's only 6:30, we can go. All right, so then there's predictable tokens. If you have a pattern, if you can log in as a few different users, you might detect some kind of pattern. Therefore, a large application might be easier to attack because you might be able to find a large sample of tokens from your own test system. So you might have sequential tokens. Here's Burp just trying payload of just 071B224870F92. Looks like just 2 characters. So it's trying just a bunch of 2 characters. And so over here, see, you've now logged in as, it was able to get a name. So a bunch of these are recognized as real users. The others don't get in. But that's the thing. If your token is short enough, you just randomly change that number and see if you hit other people's accounts. So that's pretty bad. There's colleges that have done this. There was a pretty famous case a few years back where a college student did this. You'd log into the college, and they looked right at the top, and it said, like, user ID equals, and there was their student ID number right there. So they just changed it to another student's ID number, and they were in their account. And when they told the college administrators, they tried to eject them from the school and punish them, which is the problem with telling anything about security flaws. It's called white hatting. It's very dangerous. It's like political activism. It's like telling people that something immoral is happening in politics. The most common response is to just shoot the messenger. Well, the most common response is to completely ignore you. But if they don't ignore you, they will usually blame you for complaining about it and try to shut you down or lock you up or punish you. They almost never fix the problem from somebody just telling them there's a problem. The only people that are worth talking to are people that have a bug bounty program, where they have a procedure to receive security information and handle it. If they haven't already set up that procedure, then they're too stupid to even talk to, and they will just blame you. This is a general rule. Another thing I've found is colleges that have a cybersecurity competition team, those you can tell vulnerabilities to, but you don't talk to the administration. You tell the security competition team about it, and they will communicate to the college because they know what's going on. But normal lawyers and college administrators cannot understand what you're doing when you tell them about a security problem, and they will just think you're some kind of crook trying to extort them or something. It'll have a bad result. You have to go through somebody who understands security disclosure, if you can find anybody like that. All right, so you might have concealed sequences where it looks random, but it's in fact following a pattern, dependence on time, or using a random number that's not that random. So concealed sequences are like this. This looks random. It's base64 encoded, it looks like, and it decodes to random gibberish. So at first look, you might think it's okay, but what it really is if you render them as hexadecimal numbers and calculate the difference between successive tokens, you find that it keeps being the same number. This is this 97 number, and this is the negative version of 97 number. And what's going on is this is called a linear congruential sign. What it's doing is it's just adding a large number to the token and then keeping only lower bits of the result and letting it roll over. So it appears random. This is called a linear congruential random number generator. It's not very random. Once you understand what's going on, you can draw a line between the first 2 of these and predict all the rest. And there's a script that'll do that in Python. All right. And so you can actually generate the valid tokens this way by just constantly adding this constant over and over, and then keeping only the lower certain number of bits. All right. Hello. Anyway, I'll turn this on in case you care. I don't know if you'll care, but anyway. All right, and then there's time dependency. If you're here, it's got 2 numbers, one on the left and one on the right. The one on the left just increments by 1 every time for each user, every request. The one on the right is also moving up. The high order digits are staying the same, the lower order digits are changing. So it's just moving up by a somewhat random number, but not a very big random number. So take another sample 10 minutes later, and the first number is jumped by 6, but the second number is jumped by this, and this is the number of milliseconds in 10 minutes. So what it's doing is just using a counter to count every request, and then another time counter to count milliseconds. So that means you can totally get into other people's accounts. So what you do, pull the server frequently to get the tokens, and watch this first number. So this is you making request after request, 89012. So these are all your requests. But if somebody else uses it in between, then this will jump from 42 to 44, and you'll know that number 43 is somebody else, and you know that the time must be between these times, and there's only a few hundred in there, so you can just try them all. You can predict somebody else's token. It's the kind of thing. So You have to watch it. This is why I always say you don't make your own cryptography. You have to use well-established cryptographic procedures. If you try to invent your own random number generator, you will be sorry, because stupid random number generators are not random enough. So that's a game here. Then there's a bunch of software that was written with weak random number generators. In earlier days, people didn't understand this well, and they used these very foolish random number generators. Here's the linear congruential generator I was talking about, where all they do is multiply the previous number by a constant, add another constant, and keep the low-ordered bits. So it appears to be random, but it is, in fact, just a straight line in a proper space, and you can predict the numbers. PHP. In earlier versions of PHP, it generated the session token from an IP address, the time of token creation, the microseconds, and a linear congruential generator. So once again, it wasn't random enough. And Sammy Kamkar, a very famous hacker, wrote a tool to hack into it. He did a bunch of things. He wrote a worm that spread on MySpace and so on. He's a very famous hacker. And so here's what you do. Start with the hypothesis that the tokens are randomly generated and then apply a series of tests. If you want to find out if something is random, there is actually no test for randomness, but what you can do is test for non-randomness and get that to fail. So that's the thing. You can estimate probability of this happening given that it was random, and observe if there's a pattern. You'll eventually find that it's very unlikely that it was random. So it's that's how you test it. And Burp has a thing called Burp Sequencer that will try to do some of these attacks. It will. Here's a session ID, and it's going to try to many various options of this session. It's try adding a lot of numbers to it and such. And what it will do is test many values, and it'll see how random they are. It will go over and over again, and so it'll notice the red bits are not random. So there's 32 bits, or in this case looks like 64 bits in the data, and some of them never change. So this is a way to test. And this is how you rate how good a random number generator is. You say how much entropy there is. Microsoft randomness used for address space layout randomization and such has been famously not very random. It used various things like the clock time and other things. In fact, in early versions, when Microsoft first came out with address space layout randomization in Windows Vista, there were only 8 bits of randomness. So there were only 256 possible locations. So it was randomizing that location so your attack wouldn't work, but all you had to do was run your attack 300 times, and it would then be in your expected location. So that's the problem. This with all cryptography. It's easy to make cryptography that looks good to an amateur, but isn't really good enough to stop an attacker. And then there's encrypted tokens. Again, you have a bad design goal. Now, the right thing to do is to have just a random token that doesn't mean anything, and then have a database on the server that says, when I see this token, here's which user that is. But people keep trying to put meaningful data in the token, which is dangerous. So they're going to try to build the token for meaningful data like the username. You're going to try to encrypt with a secret key not known to the attacker. That sounds good, but that turns out to be less good than you might think. Now, you might think if they don't know the key, they can't decrypt it, so they can't modify it. But that's not true, because a lot of people use electronic codebook encryption, which means they break the input into blocks like 8 bytes long, and they encrypt each block independently without reference to the others. And what that means is, this is what happens if you encrypt an image. If you encrypt this image with ECB, you get that image. The colors change, but the fact that this is a block of green, all these blocks turn into the same different green. So certain patterns are preserved. And what that means is, if your token looks like this, a random number, an app, a user ID, a username, a time, these are broken up into groups of 8 letters and encrypted. And even though I can't decrypt them, I can interchange them like blocks. I can take a block of 8 letters and flip it with another, and it will still be valid. Each group of 8 letters is encrypted. So all I have to do is arrange the length so UID equals will be at the end of a block of 8, and then find a number like the time that starts with 1, and I can change my UID to 1. So what you do is you take the blocks, 8 bits like dominoes, and just flip them around, the groups of 8 characters, until you create other inputs. And so here's an example. Here's what it looks like. UID equals is at the end of this block, and it's 218 there. So I make another user. My username is here. Username is DAF. So I change my username to, well, this is one thing you can do. You find, here's a 992. So if you flip this block with this block, then I'll move from user ID 218 to user ID 992. I'll be somebody else. So that's the first test. Just randomly flip blocks and see if you actually get into somebody else's account. But you can do better. If you carefully plan it, you can now target UID equals 1. So what you do is you, here's the time, here, instead of using, now up here, I used the name DaffyDD. Now you make another account with the name DAF1. And now you've created a block here with 1 in it. Now you flip that block with this one, you'll now be UID equals 1, which is the administrator. So this way you can control what account you break into. That's the point. Even though it's encrypted and I don't have the key, I can still perform an attack by just shuffling the blocks of encrypted data. And that wouldn't be possible if they used a better mode of encryption. All these rely on people foolishly putting meaningful data in the cookie and encrypting it foolishly instead of using proper encryption. If they really used a secure mode of encryption like AES GCM for Galois counter mode, then this wouldn't work because you would not be able to reshuffle the blocks. And so cipher block chain was an earlier way to fix this, and it had the effect of stopping this attack too. Each block depended on the previous block, so if you move them out of order, it'll no longer be valid and won't decrypt. So if you encrypt an image, it just turns into complete snow that you can't recognize, and that's what should happen. All right, so if you do that, the encrypted version appears random and no, now there is an attack on this, which we do in the cryptography class. In cipher block chaining, you take the, it turns out that you're using in your decrypting it, to take ciphertext and turn it into plain text. The ciphertext of this block is used as the initialization vector of the next block, combined with XOR. And that means I can modify 1 byte of the ciphertext, and it will destroy 16 bytes of plain text, but only affect 1 byte here. And there's an attack you use. This is called padding oracle, to crack in without the key. So that's why this is no longer recommended. What's recommended is AES GCM, Galois counter mode, is considered the strongest version of AES to use. These other versions have flaws. Anyway, all right. Here, so this is what I think the Frobber does. There's a burp attacker that will do this. He'll have a cookie, and it will just have encrypted stuff, and it will just change the bytes one by one. Change each byte as it goes through, and that will have the effect of wiping out a whole bunch of characters, making them random, but changing 1 byte here and changing 1 byte here. So most of the time, it will just mess up the data, but eventually it will change 1 digit here, UID from 216 to 226. So that's what burp does. You modify the session token, flip each bit. Here's an attack in here that does that. Your payload is flipping the bits, and it'll flip each bit in the number, and you see what happens. And so it'll take 8 requests per byte, and so you get flip the bits, and most of them are unknown users, and most of them are you, but these 2 are other people. So you just try flipping 1 bit in that token until some of them are meaningful, and there's somebody else, and that shows they've made one of these foolish mistakes. They put something meaningful in the token, and they've encrypted it in a sloppy way, so you can generate alternative text which is accepted as valid by just flipping bits. So another thing that happened is they may reuse the same encryption code elsewhere. This is very common. Somebody writes an encryptor and then they use it over and over. And so this happened to Facebook. When people would do a Facebook password reset, it would send you a link saying, click here to reset your token, your password with a long token. And somebody found that same encryption to make that token was used somewhere else, like to make the name of a picture you'd post on a page. So he was able to predict what token was going to be emailed to users and reset their password. And I think he got a big bug bounty for that one, too. All right. Let's take a look at another Kahoot. All right, good. The number is visible. we're getting. All right, so what token uses the same token every time the user logs in? This is another problem with encrypting meaningful data. If the token is just my username, then it's the same every time I log in. It doesn't change. So if somebody steals it, they can keep going back in my account over and over. These other things create semi-random numbers that change every time you log in. But if you're encrypting meaningful data, it will be the same every time they log in, which is another weakness. All right, which one do you exploit by rearranging blocks of ciphertext? That's electronic codebook, where each block is encrypted independently. All right, good. Which one do you exploit by changing a single byte? That's cipher block chaining. Changing one byte of the encrypted text will cause 16 bytes to become random, but out of the next block of 16, just one byte will change. So you can change just one letter of a meaningful sequence like a user ID or something. That's the flaw with cipher block chaining. And how about one block of data to influence the encryption of the next block? That's cipher block chaining. That's how it works. All right. All right. All right. So it's about 10 minutes to 7. I'm going to stop the recording and take a 10-minute